An elevator's motor is able to lift the elevator's passenger car full of people with a total mass of 850 kilograms at a distance of 57 meters into the air in 75 seconds. The elevator has an efficiency of 35%. How much power does the elevator demand? How much waste, I'm going to assume that's heat, is generated at the top of 57 meters. Okay, so first thing we're going to do, the idea here is we have an elevator. We're going to draw a picture. Starts here, goes up there, and it ends up a total distance of height 57 meters higher. I know, terrible picture. Not my best work. We're not all Picasso here. All right, so the work done to lift it, I'm going to call this work done to lift. It's just going to be mass times gravity times height. And in this case, I think we know all these variables here. So we're going to have mass, which is 850, gravity, which I'm going to say is 9.8 meters per second squared, and the height is 57 meters. So this is going to be the work done to lift it. So we're going to go to the Wolfram. We'll do 850 times 9.8 times, I think it's 57. We'll check. And this is 474,810. 474,810. And this is going to be in joules. So with this information now, we can find out the total power, the total energy that's used. So efficiency, I'm going to write this as a little eta, is work out divided by work in. Or to do this differently, we could say that efficiency times work total is going to give us work useful, the work that we're concerned about. In this case, the work we're concerned about is the work done to lift the lift, so to speak. So the work total, i.e. how much energy the elevator demands, not power yet, we'll get there, is going to be 474,810 divided by 35%, which is same as 0.35. So go into Wolfram, we have previous answer divided by 0.35. I'm going to round this to 1.36 times 10 to the 1, 2, 3, 4, 5, 6. 1.36 times 10 to the 6. So 1.36 times 10 to the 6 joules. All right, so now we know how much work is going to be demanded by the elevator. So now power is going to be change in work over change in time. Actually, we'll just call this work done over a period of time. So it's going to be 1.36 times 10 to the 6 divided by 75 seconds. And that is going to give us do a little thing like this, some parentheses, divided by 75, and that gives us 18,000. Oh, that seems like a lot. 18,000 watts? Maybe. 18,000, more or less, watts, which is a unit of power, joules per second. So that's how much power the elevator demands, and that's given the inefficiency, or the efficiency of 35%. Then we want to know how much waste heat is generated, and that is just going to be the difference between the work, that is the energy that's needed, and the energy that's used to lift it. So if the energy is not used to lift, but if the energy is still being produced, then it's going to be waste heat. So we'll do 1.36 times 10 to the 6, which is that, minus that. And there's I could simplify this from a math point of view, but I'm not going to. So this is our total energy. This is the energy just used to lift, and it gives us 881.8. So 881,800 joules. Let me say 881,000. Check that real quick. 881,000 881,000. Yep, close enough. So we have 881,000 joules of waste heat. All right. So I hope that helped. See you next time.